Now we're gonna try to move on and continue with our special child, which is a star load, but we're in the case where we have an open circuit, and we're gonna have a look on our question 3 and exercise, which is already an example as well, but we're just gonna have a look on the exercises. So it's all about a open circuit. And what does that mean? They're gonna specify in the problem which impedance is gonna be open. No matter where the impedance will be open, you should be able to solve. And in this case, it's our impedance ZB. ZB, it was said that it tends to infinity. Can you see? When you have a resistance or an impedance that tends to infinity as a infinity ohm, it's going to behave like a open switch. So every time they state in the problem that the impedance tends to infinity, you should be able to know that it's all about a open circuit condition of a star load. Okay? And then after doing this, then let's say, how do we solve it? And I say the most important part. Every time you have to solve your electrical engineering 3 problem is what? You start with your reference, and in this case it was EA, and then it was given as minus 240 volts. You change it to this voltage. Because of that minus, you're going to have an angle of 180. Positive phase sequence, you know already how to do your phase sequence, but I'm going to post the memo of this question in the on our website. But let's just be focused on how to approach a problem of a star load when we have a open circuit. Okay, so as we have an open circuit, we have 3 currents that are coming from the supplier. Let's observe what will be the flow of the current in our circuit. Can you see? And then in red, I'm going to use the one for the current IA. So we have a current that's coming from the supplier like this, the way I'm drawing it. Okay? On this junction here, the current can flow here because it's what? It's open. Therefore, the current will go in this direction. Can you see? Therefore, you have a current what? You have a current that's moving from A to C. Current that's moving from A back to C. Let's look again. When we take in the case of C, can you see with C we have what? A current that's coming from C, from the supply like this. IC. On this junction, the current can flow here because it's open circuit, and then the current will go back to A. And then you have another flow of current, the current that is going as C to A. So you have 2 currents that are going in opposite direction. This one is going in this direction, this one is going in this opposite direction. So you have to make a choice. Life is about choice. You need to make a choice and make sure that the one you choose, you're going to work with that all along the way. Okay? So if you make a choice to work with a current A to C, or automatically ignore that other flow of the current. Remember with Kirchhoff, you choose the flow of the current and then that's it. But when you come here, because we choose the flow of the current from A to C, which means we are going to ignore this other flow of the current. So we only want to consider this flow of the current. So we can say that this current is going in this direction. Okay? So let's calculate that current. How do we calculate it? We can see it's going to be the current AC. Okay? Therefore, our voltage is going to be what? The current is going to, the voltage is going to be what? The voltage AC as well, because if the current is moving from A to C, the voltage will move as well from A to C over. Okay? Look, when this current is coming from the supplier, you can see that we have how many impedance in series? ZA and ZC. Then series. Then you say ZA plus ZC. This is going to make an equivalent impedance. Okay? So when you have to substitute the value here, from the given voltage, you can see that this is a phase voltage because we only have 1 liter here. So you're going to times it by root 3 of what? Times of 240, okay? But what will be the angle? Look here. You have a line voltage AC, okay? What are the 3 line voltage that we always have? Is what? AB, BC, and CA. Okay? So which means we have a CA. The inverse of CA is going to be AC. Okay? So you're going to go into your phase sequence, phasor diagram, and then you take the angle of CA first. Okay? But to make CA AC, you need to come here, add or subtract 180 degrees. Then you divide by the addition of the two impedance. Okay? But remember, this current IAC is the same current that is flowing across the impedance ZA. So we can say our current IAC is the same as the current IA. Okay? This is the first step when you have to solve this problem. So, after getting our current AC, which we say is the same as the current A, okay, we are going to look the voltage drop across the impedance A, and therefore our VA, okay, is going to be, or we can call it VA, let's just call it VA, it's going to be IAC, which is the same as the current C times, okay, and then we say this current is the same as the current IA because they're in series times ZA. So after getting the voltage drop across this impedance, now I can come here and say, now I know what is the voltage VAB. Because our question here, we have been asked to calculate what is going to be the voltage of the open circuit, which is VB. Okay? Because remember, we choose A to be the higher potential. What does that mean? To be the higher potential, it means the current is moving from A to C. So this guy is the higher potential. So you're going to come now in your problem here, you remove the branch that you ignore. That's not the high potential. So you only want to remain with this part, like this. Okay? Remember, A is the high potential, which means the arrow is going to face this direction. And then this voltage, we're going to call it what? The voltage VAB, because A is the high potential part between A and B. Okay? And then here, remember the current is going from where? From this direction to this. Kirchhoff, what does that tell us? If the current is going in this direction, you have a positive, negative, which means the voltage drop will go in the opposite direction. So if you can see the current is coming in this direction, then you're going to see that this voltage VA is going to go in the opposite direction of our current. Okay? Then you come down here, you have a current B, which is coming in this direction like this. Can you see? So basically, let's make it easy. The current into a component, you have what? Positive, out of the component, negative. This current IB is coming in this direction. Into this open circuit condition, you have what? Positive, out of it, negative. Okay? The higher potential, which is say A, arrow mean what? Positive, and then here you have your negative. Okay? So we are going to apply Kirchhoff using the method of physics 2. Okay? So we know it's all about the rise voltage must be equal to the drop. Okay? What is our rise? Our rise, it simply means when you're moving from a negative to a positive. I'm rising negative to positive. Drop from positive to a negative number. Okay? So we're gonna go into a clockwise direction and collect those voltage. Can you see? Clockwise direction. When I'm coming, I can see I'm moving from a negative to a positive. I'm doing what? I'm rising. So which is gonna be the voltage VAB. Okay? This is a rise voltage. From this part, positive to negative. I'm doing what? I'm dropping, equal to VA. When I come here, negative to positive, I'm doing what? I'm I'm rising, then I can come here, I say plus. Okay, remember the I's, we have VB plus. The rise must be equal to the drop. Therefore, our unknown, which is the voltage B, is going to be